Hey, okay, got a few minutes, so thought maybe I'd try to work a example problem of an air standard dual cycle. The dual cycle, as you might recall, is a combination of the diesel cycle and the Otto cycle. I might be able to flip back through the book and find a diagram that pertains to it. Let's see. Yeah, we're getting close. All right, here's our dual cycle here, figure 923. And not sure if you can see that, so we'll take a clip of it here and paste it in. Okay, so there's our dual cycle, and we'll use these state designations even though it's a little bit wonky to have that state X in there. But that way we retain the convention that the compression ratio R is V1 over V2, which is the same as V1 over Vx. And likewise, the cutoff ratio is the same as V3 over V2, which again is the same as V3 over Vx. So both of those quantities are given here. We have the compression ratio of 18 and the cutoff ratio is 1 point, let's look, 1.1, that's what I thought. Okay, and then what else does it tell us about here? It says the pressure ratio during the constant volume heat addition process. So it's giving you some help on how much of the heat is added at constant volume. He's telling you the pressure ratio Px over P2 is equal to 1.1. So I'm going to call this RP. That's a little bit dangerous, but we can call it RP. Seems to have the same numerical value as RC. So P1 equals 90, T1 equals 18, and V1 equals 0.0003 meters cubed. And T1 is 18 degrees K. Degrees K, excuse me. Okay, so here's everything that we're given. He wants to know how much power will it produce when it's executed 4,000 times per minute. So I'm going to put here cycles per second, cycles per minute, excuse me, 4,000. Okay, so that ought to take care of it. So what do we need to do? We're going to need, he says to use constant specific heats, and so we'll do that. Maybe we'll revisit this with variable specific heats, but for now we'll use constant specific heats. So that means, for example, V, constant volume specific heat, 0.718, CP, if we need it, 1.005, and the ratio, which comes up in this analysis, the ratio of those two, we could calculate it, but it better be around 1.4. So okay, better save this somewhere. Save early, save often. It's always a good philosophy. I think I've got a place here I can stick that. So I don't know what problem number this is. Okay, so what do we need to do? we're going to need to know the temperatures at all of these points. And the idea will be to go from state to state to find them, if we can. In some cases, not this problem, but in some cases we may not know a state at all. For example, we may not know enough information to find state X, but we know that we have a constant volume process coming from state 2, and we have a constant pressure process going to state 3. And the intersection of those two processes defines a point, and we would be able to find it. But I believe we have enough information in this problem just to go station to station and find all of the states that we need. So let's look at process 1 to 2, which is isentropic. So for constant properties, constant specific heats, we can calculate T2 just from the isentropic process. T1 times V2 over V1 to the 1 minus K. Well, V2 over V1 is 1 over R ratio, and that has to be raised to the 1 minus K ratio power. And I've got this, I missed this a minute ago, so now we got that. So that says it's about 925 degrees Kelvin. The state 2 to X is a constant volume. So if we use the ideal gas equation of state, we would find out, well, let me just write it out here one time. There's our familiar area of a circle, but I'm not interested in the area of a circle. Our ideal gas equation of state just says that P1, actually we're working at state 2. I've screwed that up. Let's do it again. Alright, so P2 times V2 divided by T2 is equal to the same thing at state 3, state X, excuse me. So we can put in an X for this, X for this, X for that. That was easy. Okay, so what do we know about process 2 to X? Well, the volume is constant, so if the volume is constant, those cancel out. What else do we know about that process? He gave us this pressure ratio, Px over P2, so we know what Px over P2 is. So it looks like the only thing we don't know in here is temperature Tx. So Tx would be equal to T2 times Px over P2. Well, that's not what we called it though. We called that RP. Yeah. So I've got to get these guys on the board here. And he says that that temperature is higher than the previous temperature, and that agrees with our intuition that we've increased the pressure, we've added some heat, the temperature's gone up. So far so good. So we've got 1, 2, X. What do we know about state X and state 3? Well, that's a constant pressure process. and it's we know the volume ratio. We know the cutoff ratio, RC over Rx. So again, referring to this same equation of state, just imagine that we've got X and 3 here instead. But in this case, the pressures are the same. The pressures are the same, and the volume ratio is known. So in a very similar way here, we can calculate T3 from Tx and the cutoff ratio. Yeah, doesn't seem like much of an increase though, does it? But the cutoff ratio is not very large. But the cutoff ratio is V3 over Vx. So that seems to be correct. And now finally, to find the state 4, we'll use this isentropic process. And so a very similar calculation to what we did up here to find T2. But now the tricky part is this volume ratio V4 to V3 needs to be found. And as you'll recall, it's the compression ratio, V1 over V2, divided by the cutoff ratio, V3 over V2. So let's see, T4 then is equal to T3 times R ratio divided by RC, and we're going to raise that to the 1 minus K ratio power. And we get a result that agrees with our intuition that this temperature 4 is greater than the other temperature 1, but less than 3. So it seems to fit, and probably we've done the calculations correctly. Alright, so we know all the temperatures now, so we could find everything in the cycle if we wanted to. What's being asked is to find the power that the cycle produces when it's executed 4,000 times a minute. So it sounds like we need to find W net. We could do that one of two ways. We can either find all the work that's done in the various processes and add them all up, or we can find the heat transfers and add them all up, because for the cycle, any cycle, W net is equal to Q net. But looks like, so where's the heat transfer? Obviously 2 to X and X to 3 and 4 to 1. And where's their work? Well, there's work in 1 to 2 and 3 to 4, but don't forget there's also work done in X to 3. So it seems like either way we've got to analyze 3 processes. But let's go down the heat transfer road. What I call QH1 is this heat added at constant volume, and so that's QH1, and QH2 will be this part added at constant pressure. So for the constant volume part, it's just the delta U, and with constant specific heats, the delta U is just CV times the delta temperatures. So it looks like there's about 66 kilojoules per kilogram. H2, it's a little bit trickier because remember that's heat added at constant pressure, and because of the work that's done during that process, we have to include that work in the first law expression. And when we do, we find out that the heat transfer during that process is actually uh, related to the delta enthalpy, the change in enthalpy. And so there are the two parts to the heat transfer. In the heat transfer out, QL, is again the constant volume. So at constant volume, there's no work, and so the temp is just T4 minus T1. There we go. So Q net is equal to the sum of these things, even though I don't know what they are. And that's kilojoules per kilogram in the cycle. And just note that W net is equal to Q net. So this is kilojoules per kilogram of mass in the cycle. We now need to find out how much mass in the cycle. State 1, he pretty much gave us everything we needed to know to find the air. We need to have air, R. Pretty small number. And so what I would call capital W for the cycle is just the mass of the air times the work per kilogram. So I would call this kilojoules per cycle. And then finally he wants to know the power. And let's see, does this seem right? PV over RT. Yeah, that's the mass. And yeah, that seems right. So this is kilojoules per minute. And this is kilojoules per second, or kilowatts. And that's about about 30 horsepower. Okay, so that's a dual cycle that has given pressure ratio here to help find that temperature Tx, and the key here is just to go station to station to find the temperatures in all parts of the cycle. And as I mentioned at the beginning, it was not the case in this example, but sometimes there's you may not be able to find this temperature directly maybe you need to combine some information about this process and this process to define that intersecting process. Okay, well, that's it for this example.